And remember to put your name in on the chat for attendance, please. Okay. Just waiting for a few more to join. All right, we're almost quite a few of us already, so about ready to start. Okay, last time we were talking about how to tell a lot of different things from the periodic table, and that's what we're going to continue talking about today. We're going to even do some more exercises, more examples of what we were doing before. And hopefully that'll help you guys understand all of it. I'm also kind of updating some assignments for you. So that you'll start doing those. Hold on, I'm getting there. It takes a little while. Okay. Make sure you put your name in the chat, please. That's for attendance. Some of you have names that aren't your actual name on there, so I need to know who you are. Thank you. All right. So let's continue. All right. We were looking at, like I said, atoms and their makeup. I'm trying to find the assignments. Ah, there it is. That's the one I want to get. That's the last one I'm going to go ahead and open right now. So give me a minute. I'm going to open it right now. So you'll have a okay. It's taking a little longer than expected. Okay, here we go. And in case you were wondering, we are cutting the midterm to this last test that we're doing. That's as far as I'm going to go with your grade. So just so you know. So this is September. So it's November. I think it's okay, so it's got to be before that. Okay, there we go. All right, it's published. All right, the things that I wanted to publish are published. All right, so let me go and share my screen with you, and we can begin. Yeah, okay. Let me see here. That's okay. That should be open too. Okay. That's open. That's open. That's open. This will be open. Okay. Yep. The rest are not. Okay. Oh, I need to. No, I don't need to open that one yet. Okay, so that's that. All right, so let's look at what we have so far. Oh, there's somebody. So, okay. All right, here we go. There we go. All right, thank you for signing in. All right, here we go and sharing. All right, so the last time, like I said, we were looking at this particular PowerPoint, which is basic chemistry, and we finished it. And this time we're going to look at periodicity. So periodicity is a phenomenon that occurs on the periodic table. There's trends, and it occurs because of the way that they're organized. So we're going to look at periodicity PowerPoint next. Okay, let's download it. Come on. There it goes. All right. Takes a little time sometimes with these things. All right. Come on, open it. All right, we are just going to look at certain things, okay? Not everything that's here. We're going to look at the things that are important are our periodicity. Okay, so we're going to start with this one, which is the history of the periodic table. Okay. All right, so back in the mid 1800s, only about 70 elements had been discovered out of the, I think it's 120 now. I don't want to say too many, but I think that's correct. And they are definitely not have any more room for them. So if they discover any more or come up with anything else, it's not going to be good. All right, periodic table. Right, so it was Russian scientist by the name of Dmitry Mendeleev who actually came up with the first way to organize all of these elements that had been discovered. Sorry, it's 118 elements total, not 120. All right, so the thing about him is he actually did a great job. He was very observant and noticed different properties, and they had ideas about certain things already. So he kind of figured them out and he listed them according to increasing atomic mass and put the elements in the same columns that were familiar, that were similar to each other. And this is his periodic table from the very beginning. Remember, not all these elements had been discovered yet. So he did a pretty good job. And he actually even left some blanks for elements that hadn't been discovered. And when they were discovered, they fit perfectly in there because he knew that, the progression was so perfect that something had to be there. So he left a blank. Anyway, so then this other guy named Henry Moseley looked at the periodic table and he said, everything's wonderful except atomic mass is a little ambiguous. And that's because of isotopes. Remember, we looked at isotopes and how different the atomic masses are in some of the same elements. So instead, what he did is he organized them by atomic number, which makes more sense because atomic number is unique for every element. So, and you already know it. You've seen it. I gave you one. And you know that it increases from left to right and top to bottom. If you look at it, you can follow it. And it's just like a book. When you read a book, you go left to right and you keep going down as you get another line, right? Same thing with the periodic table. And this is why this thing that is known as periodicity, or this phenomenon that is known as periodicity, happens, because it establishes what is known as a periodic law. That periodic law is like a repetition that happens within the elements. And so they have the same physical and chemical properties in some cases. Not the same exact, but I mean, very similar. Okay, so here are the name of the families and their groups. And we kind of did these already, but I want you to go ahead and write them in if you haven't, or take a quick photo of these. That would be good, because this is a really good periodic table labeling. And you notice that group 1A is alkali metals. That includes lithium, sodium, all of those. Group
Miss
2A.
Venus, sorry.
Yes, ma'am.
Question, is this PowerPoint posted?
Yes, this PowerPoint
Okay.
is called periodicity.
Okay, thank you.
Mm-hmm. I don't know if it's available yet. I need to make sure that it is. After this, I will. All right, so the 2A, like I said, it's alkaline earth metals, and they are calcium, magnesium, all of those. Then the middle area from groups, all the Bs, right? Or if you want to look at the number that doesn't have a letter, is group 3 through 12. Those are known as transition metals. And the thing about transition metals is they can have multiple valences. Remember how we looked at how many electrons are in the outer shell? Well, in this case, this does not determine which ion that makes, not in the transition metals, because there's multiple ions that can be made in some of these. Then you've got group 3A, known as the boron family, group 4A, known as the carbon family, 5A, known as nicogens, 6A, known as chalcogens, and that's where oxygen is, and sorry, nicogens is where nitrogen is. And halogens is group 7A, and those are all of the elements that fluorine, chlorine, iodine, bromine, all of them. And then the last group is the noble gases. They're 8A. Remember we talked about how all elements want 8 electrons on their outer shell? Well, these have them. And so they're unreactive. That's what they're called. Well, mostly unreactive. That's what they're called noble gases. And then the really bottom part, which is what is really known as the cutout, because they actually cut it out. And we're going to see a periodic table that has it in it, and you'll see what I mean. Once you see that, you'll be, oh, okay, I understand now. And the inner transition metals. And if you want to go even farther, the top area of the inner transition metals, because there's 2 rows, the top row is known as the lanthanides, and the bottom, oh, sorry, yeah, and the lanthanides, and the bottom one is known as the actinides. And that's it. That's all of them. All the ones you need to know and recognize. Okay. All right, so let's keep going. Now, of these periodic properties we talked about, these are the ones that we're going to look at. Atomic radius, that is how large an atom is. Electron affinity, we'll define that later. Electronegativity, ionization energy, and ionic size. Again, that's how large an ion is. You know, so ionic size is, and you're wondering, how do they measure the radius of an atom? Because an atom is so diffuse, like a cloud. Remember we talked about that? So how do they measure it? Well, this is how. They usually bond elements of this, I mean, 2 atoms of the same element, and they measure the distance between the nuclei. And that is how they can figure it out. The difference between the nuclei divided by 2, because obviously there's 2 atoms, so that's how they do it. Okay. All right. So the first one that we're going to look at is atomic radius. Pay attention to the direction that it's talking about. It says left to right across the periodic table, we see a gradual decrease in atomic size. And you're going, wait. Doesn't that go backwards with the number of electrons? And you would be correct. That is true. But the more electrons you have, the more protons you have, the more attraction you have towards the nucleus. So it shrinks a little bit because of that. So this is what this is about. electrons are added to the S and P sublevels. Don't worry about that part, but in the same energy level, let's just call it that, in the same energy level. And they are gradually pulled closer to the positive nucleus because there's more positive protons in the middle, right? As you add more electrons. And this is known as shading, sorry. Then this is the trend right here as it increases. So it increases across from right to left. So that way, all of the largest elements that you'll have in any one period are going to be the 1As, right? And the smallest ones you'll have are going to be the 8As. And yes, look at the bottom ones, all the way down there. They're not exactly following that trend. They're kind of off, but that's why it's called a trend. It's not perfection, right? But you can kind of predict which element's bigger based on this because they pretty much follow it really well. Okay. And they increase in size going down. Now, that makes sense because remember we talked about each period increases one level of electrons. So it's like an onion. You're adding one more layer to it, right? So the onion gets bigger. All right. So that's like I was talking about, that's known as electron shielding. And that also, there's a limit to this. You cannot get more in the same volume than there's already, there's already a certain, I guess you call it finite volume that is going to be where your electrons are going to fit. That's why it's known as an electron level. And it just also interact with each other and they repel. So if you add one more, you break up that balance that you had between the protons and the electrons themselves. And now you're going to get bigger. And that's what happens. So periodic properties continued. All right. So we were talking about how the nucleus gets more protons. So it gets stronger positive force, whereas the electron cloud is getting a stronger negative force, and they're going to attract each other. And that's what happens. That's why it kind of sounds weird, but it kind of makes sense too. All right, so if you look at the relationship between the atomic radius and the atomic number, it is exactly an opposite, exactly inverse relationship. And there's all your top ones, as I told you, lithium, sodium, potassium, rubidium, cesium, and francium are all 1As. And all the bottom ones down there are all the ones that are in group 7 in this case. But there's also the noble gases in this one. Okay, so the next thing we're looking at is ionic size. So remember I told you that when you have a metal, it's going to lose electrons, right? Always. So if you lose electrons, the charges that are positive are going to win, basically, right? This race. And they're going to pull those electrons even closer to that nucleus because now there's less of them to repel each other. Therefore, the sodium ion is going to decrease in size. Plus, on top of that, you're removing a whole entire electron level when you remove the one electron that's on that third level. I mean, in this case, it's sodium, so it is in the third level, yeah. All right. So this is what you have to remember. Okay, why is it not moving? This is weird. Okay, here we go. Oh, there we go. Oh, that was strange. It just, okay. So that's what I was talking about. Okay, so now let's look at the opposite. When you have a non-metal, and non-metals are the ones on the right of the periodic table. Remember on that little stair step, except for the metalloids that are in the middle, but we know which ones those are because we talked about them too. So now you have an ion that has an extra or many more, I don't know, depends on which ion it is. But in this case, chlorine gains 1 electron, but it doesn't gain any protons, right? So now you have more electrons in that same level, and they're going to repel each other more because now the balance between the nucleus and the electron cloud is different. And the negatives are winning, therefore the cloud gets bigger. All right. Okay, so let's look at the trend right here. And if you look at it, all the yellow or beige, whatever color you see, are the metals, and all the green are the non-metals. Okay. All right, so when you look at this, you can really see the trend. Now, notice in the middle area, when there's more than one ion, what is happening? What do you see? What trend do you see? Look at chromium, for example. Chromium 2 plus and chromium 3 plus. What's the difference? Somebody can tell me. I'm sorry?
Did it gain an electron?
No, it didn't gain an electron. It lost another electron, right? Because remember, positive means losing.
Right.
Okay, so it lost another electron. And what do you see about the size?
It decreased.
Right. So the trend is the more electrons you lose, the smaller you get. Do you see that? Look at copper. Copper has the same thing. Copper is quite obvious on this particular. See, there's your atom on the top, the one that's in red, right? And then you got the copper plus 1, which is 96 ppm. And I'm not ppm, sorry. What is it? I forgot the name of it. Is it PM? Picometers? I think it is. And then copper 2 plus is 73. So it goes from 128 to 73 once it loses 2 electrons. You see that? So that is how it works. The more you lose, the smaller you get. And the other ones don't ever gain 1 or 2 or 3. They just gain the amount that they need. They either gain 3 or 2 or 1, right? So they don't have any in-betweens like these other ones, like these transition metals. All right, so let's keep going. All right, the next periodic property, remember. Oh, never mind. Okay, so let's skip this part because you don't know anything about this part yet. And we're gonna skip it completely. Okay, so now the next periodic property is ionization energy. What is ionization energy? It is the energy needed to remove one of an atom's electrons. Or if you want to look at the reverse definition of it, is how strongly an atom holds on to these outermost electrons, okay? So once you see that, you can tell, all right? Now, when you look at this, the higher the ionization energy, the harder it is to remove, right? Okay, so in this case, we do include the noble gases. Normally, we don't include the noble gases because they don't react. But this one is different because noble gases are already full, and they're going to be the ones that are not going to want to let go, right? So it's going to take a lot to get those electrons off of them. So they normally don't form ions. So you would have to actually force them off of there. But chlorine, and they want to gain, not lose. So obviously they're going to hold on to their electrons. So it makes sense that the ones that only have one are going to want to get rid of them faster. Therefore, the lowest ionization energy is going to be on those that are on group 1A. And the highest is going to be all of the noble gases, as you can see. You see that? All right. So the trend goes exactly the opposite as atomic radius. It goes from left to right and bottom to top. And it makes sense that it goes from bottom to top also, because if all you have is one electron or two electrons or three electrons, right? Well, three electrons, you are going to want to get rid of it because you're full already if you get two. But anything that you have just as less electrons rather than 20 electrons, right? You have only two electrons. You're going to hold on to your 20 a lot stronger, to your 20, to your 18, sorry, a lot stronger than you are your helium. Because like right here, helium has two little electrons. Look how high it is. And that's because it's full. Remember that the first level only can take two, right? And so helium has its two, and it is 100% full. And it only has two, so it's not going to want to let go at all. Now, neon has 10. That's fine. It's full too. Argon has 18. Krypton has 36, which means its outer layer is also full. Xenon has its 54, and radon has its 86. All of those are full. But since there's more electrons, you notice the trend decreases, right? Okay. So pay attention, and I would be drawing arrows if I were you in my notes. All right. So the thing about ionization energy is those atoms that lose more than one electron are removed one at a time, not all three at once or not two at once, okay? So you can actually measure the amount needed after each removal. So basically, if you take electron, let's say calcium, you take electron 1 off of calcium, then you can take, or magnesium, it takes a little more energy to take the second electron. In the core electrons, you notice this little blue area with the stair step, how it's increasing? There is no way to remove those because remember, nature forms anything that doesn't spend as much energy. So when the amount of energy is too much, and this is almost 10 right here in sodium, if you look 10 times, it is not going to happen. And look at magnesium, it's over 10 times with the first one. You see that? So it is not going to happen. So you are never going to see a sodium plus 2, a magnesium plus 3, and aluminum plus 4. Okay? You're not. So whenever you are doing any compounds, it actually has to do, you have to make it realistic. In other words, you can't say NaCl2 because there's no sodium that drops 2 electrons. There's only one. It only drops 1. Okay? So should always describe the way that they actually exist in the most efficient way possible. And by that, we're talking about energy conservation. We don't want to spend too much energy making these compounds. Okay, so our next periodic trend is electron affinity. And electron affinity is defined as the measure of the ability to attract or gain an electron. Okay, so an atom attracts or gains an electron, and we're measuring how strongly. Okay, so this is, remember, metals, nonmetals. So obviously the metals are going to be the lowest electron affinity, right? Because they don't attract an electron, they give it. And the nonmetals are going to be the highest. So again, and also the closer it is to having a full outer layer, the more likely it's going to be looking for it. So it's going to go even higher. All right. So that being said, the noble gases are not even in here. We do not even talk about the noble gases because they're right at the bottom. See, so the trend doesn't work if you talk about the noble gases. So you have to exclude them in this particular trend. But you got fluorine, chlorine, bromine, iodine, and astatine. All of those are in group 7A, known as the halogens. And they are the highest. And that makes sense because they have 7 already. All right, so remember, we are looking to fulfill the octet rule, which states that an atom will gain or lose or share, because there's also covalent bonds, electrons in order to acquire a full set of valence electrons. And a full set is 8. And we will look at this S and P later, but remember, according to that Bohr model we looked at, 8 electrons is in every shell, including the outer shells. Okay. And here you go. These are some Bohr models showing you kind of how when they gain 2 electrons for oxygen, for example, it becomes the oxygen ion, or the oxide ion, actually. The fluorine atom gains an electron, it becomes a fluoride ion. Sodium loses 1 electron, and you notice that now it has 1 less level and 1 less electron, and it is now the sodium ion. And magnesium loses 2 electrons that it has on its outer shell, and it now becomes the magnesium ion. And if you look at every one of these that we mentioned, they all look like neon because they're all full, like neon is. See, the oxygen atom now looks like neon once it gains it. And the fluoride ion also, right, looks like neon once it gains it. And so does sodium and magnesium because they lose that extra level. All right, we're not talking about those just yet. All right, next one is electronegativity. This is the most important trend for compound generation or compound formation, because if you remember the definition for electron affinity, the words are word by word the same except for an addition at the end. You see that? In this case, it attracts them into a chemical bond. So electronegativity reflects the ability of an atom to attract electrons in a chemical bond. And fluorine is the most electronegative element, and electronegativity decreases moving away from fluorine. So if you're moving away from right to left, right, it's decreasing towards the left. If you're moving away from flooring towards the bottom, then it's decreasing down. So basically the trend is exactly the same as what we talked about before. And it also correlates with an ionization energy and the electron affinity. Therefore, the trends are the same. They go on the same direction, which is they increase from left to right and bottom to top. And here's kind of like a last look at those trends. And then you have metallic and non-metallic character, which makes sense that they increase towards the upper area of the right side of the periodic table if you're non-metal, right? Because all the non-metals are on that side. And it decreases towards the bottom lower area of the periodic table on the left because those are metals. And the metallic character is the opposite because metals are on the left side and non-metals are on the right. So it just makes sense. All right. So that is all of that. Let's not look at the boiling point. That gets kind of confusing when you don't know certain things. So let's not look at that. All right. So now let's go practice a little bit. All right. So what I'm going to do is I'm going to bring up the periodic table. Okay. And I'm going to give you some metals and you're going to put them in the right order on the chat based on the one thing that I'm going to tell you about. In other words, if I say electronegativity, then you're just going to put them in order of electronegativity, increasing always. Always make it increasing order. Let's see, where are you? I don't want to pass it, so that's why I'm going so slow. All right, there it is, color periodic table. All right, so I've got the periodic table, and let's get those trends going. All right, let me make it bigger for you. Oops, that's big, too big. All right, now let me get this thing. Okay, you can see that okay? All right, so let's go. Let's look at periodic table trends on this one. All right, so if I ask you, first of all, remember the names. So we're gonna do like a matching. Remember the names of the columns, right? I mean, each one of the period, not the periods, I keep saying periods, the groups of the periodic table. Okay, so if I give you an element, you're going to tell me what group it belongs to. And don't say 2A or 1A, but that's not the name. I need the name. All right, so strontium. And I'm going to point to it with my, hold on. I'm going to point to it with my spotlight so you can see it. All right, that's strontium right there. Okay. Anybody? What's the name of that group? We started with
It's
it.
group 2.
Group 2, yes, but what's the name of it? It has a name.
You mean like 2A?
No. It has an actual name. Known as the something metals.
The earth metals.
Alkaline earth metals. Very good. Yes, alkaline earth metals. All right. I'm going to now put one here, chromium. What is that whole entire group, the yellow group, known as? Yellow group in this periodic table. Not always a yellow, but what is this whole area called? But we're talking about chromium. No, nobody? It is known as a transition metal. Remember? All right, I'm going to point to iodine. What is that column called? I've mentioned it several times. Nope, nobody.
Reactive,
Mm,
hold on. Reactive non-metal.
no, this whole
No. It's the A1.
Halogens.
Yes, that.
Halogens. All right.
Sorry.
No, that's fine. This one, where nitrogen is, they have a weird name. See, you need to learn these names. That's why I'm pointing out that that's kind of how it's going to be on your test. You're going to have an element and you're going to have to name the group. This group is known as nicogens. Then we have argon, which is over here. What is this name? These are known as the...
Argon is the noble gases.
Yes, very good. And rubidium over here?
You said rubidium.
Yeah, see, I'm pointing
red.
to it. Yeah.
That'll be an alkali metal.
Alkali metals, yes. And
Alkaline,
last
sorry.
one, silicon.
Silicon.
What would that one be called? The group that it belongs to. This one's kind of easy because...
A metalloid?
Yeah, that is true, but it's the whole column that we're looking at. This is known as the carbon group. See, because carbon's on top. This is the boron group. All right, and that's it.
Wait.
Gonna do that real quick.
So it wouldn't be a metalloid?
It is a metalloid. It is also represented. There's several hats this one fills. It is a metalloid. It is a representative
non-metal
element. It is not non-metal, not if it's a metalloid. And it is a carbon group member. So all those things, yeah, there's a lot of stuff. So, you know, this silicon is busy.
Okay, I think I'm following.
Okay, so basically what we're looking for is, let me see, do I still have that PowerPoint or did I close it? Please tell me I didn't close it. No, I didn't close it. Well, I might have closed it. But that one thing right here, this, what we started with, this one, that's what you need to know. Okay, see how their names are right there? And like I said, I'm gonna make sure that this PowerPoint's available to you here shortly, because I haven't done that yet. But
so this will be color coded to the periodic table.
Yes.
Okay, got you.
That's right. They're the colors that kind of tell you what they are. Okay. All right, and that's it. We're done. Next time we'll do another little activity where I'm going to give you an element and you're going to tell me how many valence electrons, what groups, what groups it belongs to, like metal, alkali metal, whatever, that kind of stuff, and what ion it makes. All of those things. Wow, huh? Okay. But not until Monday. So we'll see you then.
Okay, have a good day.
You too.
You took the roll, right? My name on the roll?
Yes, definitely.
Okay,
I
thank
have
you.
it. No problem.
All right.
Bye-bye.